section 6.2 today. And we're going to talk about figures in space. So let's review really quickly. When we talked about we were talking about just flat being in the plane, and we had some shape that had some number of sides, didn't matter how many, and all of our sides were segments. What did we call a shape like this? Well, what do we call a shape? What do we call a shape that just had some shape that had four sides? Quadrilateral. So quadrilateral is four sides. Triangle is three sides. So what do we call a shape that had just some number of sides, just a bunch of sides? Polygon. So a shape with a bunch of sides is a polygon. So poly means many, and gon had to do with the angles. A polygon. Well, in three dimensions, in 3D or in space, however we want to think about it, we talk about, it's a similar word, polyhedrons. So our most general shape, and we'll kind of nail it down what the details are, but our most general shape is a polyhedron. So let's talk about what makes up a polyhedron. I want to get rid of this. A polyhedron is a closed solid made up of polygons. So that's what we're going to be talking about for part of chapter 6 and 7, is these closed shapes made of polygons. The polygons are called the faces. So the polygons are the faces of our polyhedron. The faces meet at edges. And we call the corners are the vertices. So let's draw a really simple polygon. So here's my polygon. So there's my polygon. So this would be a face. This would be an edge. And each corner would be a vertex. So that's what we're talking about when we're talking about polyhedrons. So this is a simple polyhedron. We can have more complicated polyhedrons. This is a simple one, so we can talk about the parts. When we talked about polygons, what did we mean when we say we have a regular polygon? All sides and angles same. Perfect. So what would you guess we mean when we talk about a regular polyhedron? So sides and faces and angles are the same. So that's essentially it. But we can kind of simplify. We can simplify that and say that for a regular polyhedron, we have the faces are congruent polygons. So our faces are congruent polygons, and the same number of faces meet at each vertex. So this is enough to guarantee us that we have a regular polyhedron. If all the faces are congruent and the same number of faces meet at each vertex. All right. So having congruent faces, having all of our faces be congruent polygons, and having the same number of faces meet at each vertex guarantees us that we have a regular polyhedron. But the idea is the same, that the shapes are the same, the angles are the same, the sides are the same, all that kind of thing. So any questions about polyhedrons? And we'll talk more about different kinds of polyhedrons as we go into the chapter a little more. All right. Next thing we're going to talk about is lines and planes in space. So far we've talked about points and lines and angles and all different kinds of things in the plane. So now we want to talk about these things in 3D. First thing that we're going to look at is parallel planes. How would you guess, what would you guess we want to happen with parallel planes? What would have to be true about them?
Parallel.
They're parallel, which means what? Well, parallel means, and we're talking about planes, so planes really don't have a size, they're infinitely large. What is when we talk about parallel lines, what was true about parallel lines? They never touch, they have the same slope. What else? Someone said something else? And what did we touch? So they have the same slope, they never touch. What was the kind of math word that we use for when lines touch? Intersect. So they never intersect, right? So what would you guess we want to be true about parallel planes? They never intersect. That's how we're going to define two parallel planes. Planes are parallel. If and only if they never intersect. An example, so thinking of this room and thinking of the parts of the room being parts of planes, what would be an example in the room of parallel planes? The opposite walls, right? Or the floor and the ceiling. And at least we hope that's the way that the building was made. One time, a long time ago, I had a job where I delivered furniture, and I delivered a corner bookshelf to a dome house.
Well, keep saying yours.
Yeah. Yeah, so they delivered a corner bookshelf to a dome house. There weren't really any corners in there. So anyway, thinking about parallel planes made me think of the dome house because the walls weren't parallel anymore. So opposite walls would be examples of parallel planes. Floor and ceiling would be examples of parallel planes. Next thing we want to figure out is when a line is perpendicular to a plane. Well, before we go talk about this idea, what do we mean by perpendicular? Oh, yeah, so Angelique's doing this. So that's the right idea. What do we call that? What's our angle? 90 degrees, right angle. Perpendicular means 90 degrees or right angle. So we want to know when a line makes a 90-degree angle with a plane. We have to be a little bit careful. We have to be a little bit careful with this one. And I'm going to erase this. I think it's okay. So we're going to say a line is perpendicular to a plane if and only if well, let me back up here. I'm gonna back up a little bit, and let's talk about this for a second. For a line to be perpendicular to a plane, what has to be true about the line and the plane? What's that? Well, they have to be a corner. So what do they have to do? Intersect. They have to intersect. The line and the plane have to intersect for the line to be perpendicular to the plane. So the reason I backed up is I'm going to say a line is perpendicular to a plane at point P because they have to intersect at some point if and only if the line is perpendicular to every line in the plane through the point. So let's draw a picture of what we're talking about, and then I'll explain why we had to be careful and write it the way we did. So here's my picture. There's my plane. Here is my line. And we want that to be perpendicular. So there's point P. That's where the line and the plane intersect. And I'm going to draw in a couple of lines through point P that are in the plane. So there are a couple of lines in the plane, and what we're saying is that this line has to make a 90-degree angle with all of these lines that go through that point. And the reason is, if I draw this line up on the board here, like so, and I take this line of markers, and I'm going to say that this is going to be perpendicular to the plane. Well, one, it has to go through. It has to intersect the plane. Well, I can rotate this line of markers around this line at any angle, and it still makes a 90-degree angle with that line. As long as I'm not turning it this way or this way, it still makes a 90-degree angle with the line. So if I'm rotate it down here, it still makes a 90-degree angle with the line, but it doesn't make a 90-degree angle with the plane. To make sure it makes a 90-degree angle with the plane, I have to make sure it makes a 90-degree angle with every line that goes through that point where they touch. So that's why you have to be careful that way. You have to make sure that we can't rotate this line around and have it be perpendicular to the line but not the plane. So that's how we guarantee that a line is perpendicular to a plane. So questions on that one? All right. Next, we're interested in when a line is parallel to a plane. So we were just talking about things that were parallel. What are we going to guess needs to be true about this line and this plane for the line and the plane to be parallel? They don't intersect. So in parentheses I'm going to say never intersect. Well, we want to be able to guarantee that our line never intersects our plane. Well, what's something that we know that a parallel line, that a line, if we have two lines, what guarantees that? Let me think how I want to say this. If we have two lines, what guarantees is that those lines don't intersect? That they're parallel, right? So, do you think it would work if I said that if this line that I'm interested in is parallel to a line in the plane? Would that make the line in the plane parallel? Does that make sense? So I have this line above my board here, and I have the line of markers out here that I'm holding. If my line of markers is parallel to that green line, is the line of markers going to be parallel to the plane? Is it ever going to intersect the plane? It can't go towards it because eventually then these two lines wouldn't be parallel. Can't be tilted this way because then the two lines wouldn't be parallel. So if I make the two lines parallel, one above the plane and one in the plane, that makes sure that this line that I'm making with the markers here, holding them together, is not going to touch the plane. So that's how we guarantee that a line is parallel to a plane. If and only if it's parallel to a line in the plane. So our picture there would be, here's my plane. Here's my line. Here's my line not in the plane. So this we'll call line 1, line 2. So 1 is parallel to line 2, so line 1 is parallel to the plane. So as long as this line is parallel to a line in the plane, then our line is going to be parallel to the plane. All right, questions about when lines are parallel to planes? All right. Let me ask you a question about two lines now. So we're not on the plane anymore, we're in 3 dimensions. Can we have two lines that never intersect but are not parallel. So we're in space. We're not on a plane. Because in a plane, if two lines don't intersect, they're parallel. But now we're in 3 dimensions. Can we have two lines that never intersect but are not parallel? Brody says yes. Stephanie says yes. What would be an example of two lines that aren't parallel but don't intersect? Anybody have an idea?
Well, if you have one line forever going this way and one going this way, because they're parallel.
Okay. So, but now think, so what would guarantee that they don't touch? We're in 3 dimensions. Did you have an idea, Becca? What if one's going this way and one's going this way, but this one is up here? So we're in 3 dimensions now. So the example that, so if two lines are at a different level, different height, we could think of different height. So what I think of is me walking along the floor in this classroom and someone walking along the floor in the classroom below us in the opposite direction. We're not going to run into each other. So we can have two lines that are not parallel and never intersect when we're in space, when we're in 3 dimensions. We call those lines skew lines. Skew lines never intersect and are not parallel. So we can have, and you could think of airplanes flying. You could have two airplanes flying in different directions. As long as they're at different altitudes, they're not going to run into each other. So that would be an example. Their paths would be examples of skew lines. Last thing we need to talk about today is what we talked about in the opener. The dihedral angle. Dihedral angle just means the angle between two planes. So our example from our opener was the floor and the wall. The angle was 90 degrees. So the dihedral angle between the floor and the wall is 90 degrees. Di just means two, and hedral, we talked about polyhedrons, talks about the faces. So it's just the angle between the faces, so angles between planes. So, talking today mostly about terminology and just about some basic ideas of working with shapes in 3 dimensions. Any questions before we stop? All right.